This is a video on section 6.8 in the textbook about molecule shapes and polarity. So the molecule shape is determined by how many things the central atom needs to make space for. So in this picture I have a blue O as the central atom, and if the atom needs to make space for two things that are around it, then those two things can be 180 degrees apart. So almost like a sphere or a circle cut in half. So it's a line. It looks like a line. All right, if the blue circle needs to hold three things as far apart as it can, if it needs to make space for three things, then the biggest space that it can have is 120 degrees apart. So it's almost like a pizza that's been cut into thirds. So if you draw a circle that goes through the three black dots, it's like a pizza that's been cut into thirds, like a flat pizza. And each piece is 120 degrees. So if you need to hold four things as far apart as you can actually get bigger than a pizza cut into quarters. So pizza cut into quarters would be 90 degrees, but if you use all three dimensions, you can get them farther apart. You can get them 109 degrees apart. So I've tried to show this by the circle in the middle is holding two black dots sort of above itself, one off to the left and one off to the right, and then the two black dots that are being held below the blue circle, one of them is supposed to be coming forward out of the screen and the other one is going backward into the screen. That's why I made one of the dots big because it's closer to you, and the other dot I made really small because it's far away from you. A little bit hard to see on a flat slide though. So what things are we talking about? What would the central atom need to be holding and making space for? The total number of things are the number of atoms that the central atom is bonded to, plus the number of lone pairs it's carrying. Because the atoms, the bonds to the atoms are made out of electrons, the lone pairs are made out of electrons. Electrons don't like to be near each other, so they get as far away as they can from each other. So we can't count the bonds though, we have to count the atoms, because if there are multiple bonds to the same atom, those can't be in different spaces. You can't have a bond to an atom 180 degrees away from another bond to that same atom. If a couple bonds are going to the same atom, they have to be in the same space. It just works out that way. So we have to count the atoms, not the bonds that the central atom has. So as an example, I gave water. The oxygen is the central atom in water, and that oxygen is holding on to four things, two hydrogen atoms and two lone pairs. If you draw out the Lewis dot structure, you'll be able to see that. All right, so this is a summary of the different shapes that things can have. It's also located in a table in your textbook on page 215. So the first example, carbon dioxide, the central atom is carbon, and it's holding on to two atoms, and it has 0 lone pairs on that carbon. So it's making space for two things, and it's holding those two things, those two oxygen atoms, 180 degrees apart. It's a linear molecule. The next example is actually formaldehyde. The carbon is in the middle. It's bound to three atoms, the one oxygen plus the two hydrogens. Again, carbon does not have lone pairs, and so the total things it's holding is 3. So that looks like a flat pizza cut into thirds. The angle is 120 degrees. And that shape is called trigonal planar. The SO2 molecule is kind of an unusual example because it's something that can have one lone pair and be bound to two atoms. So it's holding three things, and the three things have a 120 degree angle between them, but since one of the things is a lone pair and you can't really see it that much, it doesn't really look like a pizza that's been cut into thirds. Maybe it looks like a pizza that has 2/3 missing, and so it's a bent molecule. These last three examples, methane, ammonia, and water, are all molecules that have four things around the central atom. So notice that the number of things corresponds to the angle. So the four things all have a 109 degree angle, just like the three things both had a 120 degree angle. The difference with the 109 degree angle is, again, if it's a lone pair, it's hard to see the lone pair of electrons. Electrons are tiny, and so it doesn't look as much like a tetrahedron. The only one that looks like a tetrahedron is methane, where there's 4 atoms. Once there's 3 atoms, it looks like a tetrahedron with the top cut off, which kind of looks like a pyramid. And when two things are cut off of the tetrahedron, it just looks like a bent molecule. All right, so shapes have to do with the polarity of molecules. Bond polarity we already talked about in section 6.7. Whether a bond has a negative end or a positive end. If the bond is evenly shared, then there's not really a negative end and a positive end. That's a nonpolar bond. And if all the bonds in a molecule are nonpolar, then the molecule overall will be nonpolar. There's no reason for it to have a negative end and a positive end. If a molecule has polar bonds, then we have to look at the shape to decide whether it's a polar or nonpolar molecule. Because it is possible for a molecule with polar bonds to still be nonpolar. So how does that happen? Well, if the dipoles, the polar bonds pulling in a certain direction, if they're all arranged in the shape of the molecule so that they pull evenly in all directions, they're going to cancel out. So if the shape of a molecule is symmetrical, then even though it has polar bonds, the overall molecule will be nonpolar because there's not a negative end and a positive end, or a negative corner and a positive corner, because it's evenly distributed, and so there's not really a polarity to the overall molecule. So some examples, carbon dioxide, there's an oxygen on either end and they're pulling in opposite directions, so that's symmetrical, it cancels out. And carbon tetrachloride is a tetrahedron shape. The chlorines are all pulling on the electrons of the carbon, but they're all pulling evenly in all the different directions, so there's not a negative edge or a negative corner of that tetrahedron. So if the dipoles are not symmetrical and they're pulling towards one end or towards one side, then overall the molecule will have a more negative side and a more positive side. And overall the molecule will be polar. So water is an example of that. The oxygen is more on one side of the molecule, the hydrogens are more on the other. So there has a negative side of the molecule where the oxygen is and a positive side where the hydrogens are. The same thing with ammonia. There's a negative end where the nitrogen is sticking up, the nitrogen is more negative. Where the hydrogens are sticking down, the hydrogens are more positive. So overall the molecule has a polarity, has a positive end and a negative end. All right, so this flat two-dimensional PowerPoint I don't think is a good way to do justice to the shapes of molecules. I think I've done my best with this topic, but the pictures in your textbook are shaded and drawn very artistically, so they are a better 2D representation of what I was trying to explain to you. If you look at the pictures and the charts in your textbook, the tetrahedron shape is pretty cool. The best way is to take a little bit of time to play with a model kit. There's one on reserve in the library, not near the bookshelf, but there is an item shelf where they have anatomy models and rock kits. So it's with the rock kits because it's a flat box, just like the rock kits are if you ask in the library for them to lend it to you for a couple hours. Or this chemistry stockroom also has some model kits. And Matt said he's willing to let you work with some in the hallway outside of the stockroom window if you come by while he's there and ask him for some. Also, if you are planning to go to office hours with a different chemistry professor while I'm gone, if you email them or call them ahead of time and say, hey, I'm going to come to your office hours tomorrow and I really need help with the shapes of molecules, would you please have a model kit available? I think they would probably be willing to do that if they know ahead of time. They probably won't leave their office hours to go find a model kit, but if you let them know ahead of time, they might be able to do that for you. So I hope that you were able to look at some three-dimensional shapes of molecules and get a better sense of this.